All right, so welcome to another episode of this Deep Learning with Pytorch series. And we are continuing our discussion on the convolutional neural network, right? So in the last few videos, we talked about what are the building blocks of convolutional neural network and how each of this component work, the building blocks, and also how we can implement a convolutional neural network using PyTorch, right? So far you may be having a confusion that how to select the number of uh, filters, what would be the shape of those filters, when we should use the pooling, and what would be the stride. So all those confusions at this point you might be having, right? So just to tackle those confusions, we can take help of the architectures that has been built by the scientists so far. Like they have explored some of the architectures which generally works well across different type of image classification problem. So we can borrow those concepts and those architectures and use in our practice, right? So first of all, like we will talk about AlexNet 5, so which is a neural network, the convolutional neural network architecture, which was built on top of grayscale images. So the input image was of a shape 32 cross 32 cross 1. So here the input image was grayscale, so only one channel was present. And then like we ran through a filter of like 5 cross 5, and we had six those filters at the first layer. So the output comes as 28 cross 28 cross 6, right? Then average pooling was done. So that time like people used to do more the average pooling. Now you will see like people generally use the max pooling. And once the average pooling is done, the size got shrink to 14 cross 14 cross 6, right? Then another layer of convolutional neural network was convolutional operation was introduced, which is like we are running through a 5 cross 5 filter, and we ran 16 filters on top of this 14 cross 6 filter, right, with a stride of 1. So the output was like 10 cross 10 cross 16, right? Then again average pooling, and in the end we have introduced fully connected layers, and at the end we will have a softmax layer which will have which will be doing uh, a 10 class classification, right? So this was like a very basic architecture where we had like around 60,000 parameters. Then the another architecture which was quite famous was like AlexNet. So it worked on the colored images where the input images were shape of like 27 cross 227 cross 227 cross 3, right? And then we kind of ran 96 filters of shape 11 cross 11 with a stride of 4, right? And we kind of got an output which is like 55 cross 96, right? So this was the output, right? And then we have introduced a max pool with a 3 cross 3 filter and with a stride of 2, and we got an output of 27 cross 27 multiplied by 96, right? Then again we run same convolution of size of 5 cross 5, and we got a same size of like 27 cross 27. And in this layer 256 filters were used. So the total number of output, the total after doing all this operation, the output of the image was like 27 cross 27 cross 256. Then few max pooling operations. So after all that, the last image, the last extraction of this operation was like this, which has an output of 6 cross 256, and then the few fully connected layers. And in the end, we were doing a 1,000 class classification. So that's why a softmax with 1,000 classes, right? So these are the very basic architectures which is generally present, and which we can like borrow some of the concepts out of this. Okay, now moving on. So here, this was like a quite the size was quite reasonable, and around 60 million parameters were present in the AlexNet, right? Then we have another famous CNN architecture, which is like VGG16 which also works on the color images on the shape of like 224 cross 224 cross 3, and we run through like two convolutional layers back to back. So you can see here like a convolutional layer, like 64 filters with a shape of like 3 cross 3, and that has been run through twice on top of this image, and we got an output of like 224 cross 224 cross 64 because there were 64 filters were present, right? Then we are doing pooling. In the pooling layer, we kind of reduce the size of by half, and we get a the shape of like 112 cross 112 cross 64. And the max pooling that we were doing here was like we the filter size was 2 cross 2 and with a stride of 2, right? Then again a convolutional layer with 128 filters were done twice, and again a pooling layer, then again a convolutional layer with a 256 filter was convoluted thrice, and a convolution operator with 512 filters were passed through again thrice, and we got an output. Finally, we have certain fully connected layers. Like the first fully connected layers were there were around 4096 number of neurons, and then again a fully connected layer with 4096 neurons, and in the end we were doing a 1000 class classification, so a softmax with 1000 classes, right? So here if you see the trend here, like the height and dimension kind of getting shrinked in every operation, but the size of the channel or the number of channel got increased with the increasing operations, right? And there were around 138 million parameters that were present in this VGG16. And generally, like we will discuss a concept like transfer learning. So in case of transfer learning, we can use either of this architecture, and then we can like fine tune the architecture according to our need, and we can fit into our problem, right? So the last architecture which I wanted to talk about was ResNet, right? So where there was a concept called residual block. So if I take an input, right? So if my input is like AL, so particular layers input is AL, then we kind of do the linear operation where we multiply the W with the AL, and then we add the bias and we get a term which is ZL plus 1, right? So which is after applying the linear operation. Then we pass through an activation function. So generally this activation function is nothing but ReLU, and we get an output of AL plus 1, right? So activation after applying a set of linear and non-linear operations, right? Then again, we do a linear operation when we get like ZL plus 2, and after applying another non-linearity, we get the AL plus 2, right? So this is generally the basic step which we do any when we are doing any operations, right? But the concept which got introduced to residual block here is that we kind of get our ZL plus 1 using the AL, then we get the AL plus 1 and the ZL plus 2. And once we have the linear operations at the second layer, then what we will do is we will introduce a skip connection where we will add back the AL from back to the previous layer, and we introduce that activation before applying the activation function, right? So we add our ZL plus 2 with AL, and then we pass through an activation function, right? And finally, we get the output, which is AL plus 2, right? So this is kind of a skip connection which we introduce in this block, and that connection we generally call as skip connection. Now, what are the benefits of using a skip connection, right? So if I just get the final output here, and if I assume that my ZL plus 2 is kind of having a value of 0, then if I use a ReLU activation function, and if my AL is at least a positive value, then at the after doing the operation at the AL plus 2, that is after doing the operation at the second layer, we can at least get back the identity image, right, or the input image, right? So if this whole part is cancelled out and that is getting 0, then we can get back at least the L. So if this gets cancelled out and gets 0, so we will this AL plus 2 will be equals to AL, right? So which will at least give you back the input image that has been passed, right? Now, why do we need a skip connection, right? So it has been seen that if you are introducing more layers into the network, like with the increasing number of iterations or epochs, your training error gets kind of stagnant if you introduce more layers, right? So if you see here with 20 layers, your training error is also kind of getting decreased here. But your when you are using a higher number of layers, your training layer is kind of getting stagnant here, right? So which is the problem here, and that we tackle that problem using this skip connection by introducing the skip connections, which are like this. We will kind of add back the previous input so that if there is any problem related to vanishing gradient or any other problem where the learning is not happening properly, at least we will get back the previous layers input, right? So with that, we kind of hope that your with the increasing number of epochs and with the increasing number of layers, your learning will be much more smoother, and we will your network with deeper number of layers will work well, right? So that is the concept of introducing a residual block, which will kind of stabilize the learning, and which will by increasing the number of layers will not affect the training error, right? So training error will also kind of get decreased with the increasing number of layers or epoch, right? Okay, so the last thing which I wanted to talk about was transfer learning, right? So all this we have talked about, right? This type of architectures like the VGG16, right? So if you see here at the output layer, we are doing a 1,000 class classification, right? So it may not be the case for your use case. In your use case, you may be doing a 3 class classification or at max 10 class classification, right? So what you can do is you can throw away this part, and you just throw away this part and add another fully connected layer, and you can introduce a softmax based on your use case, right? So this classifier you can add back here, a new classifier you will add, and this you will throw away, and that you can so you can adopt this architecture to your use case, right? So if I just go back to this concept, where whatever you can do is, this is the first thing which I wanted to talk, like you have your CNN base, then you add your fully connected layers, right? And you will not touch the weights of this CNN base, and that will be frozen, right? So this part will be frozen, and you will only train or touch the weights that are associated with this fully connected layer, right? So this will you will freeze, and you will only do the weight updates in this fully connected layer, right? So so in this way, you will kind of adopt the architecture of the CNN base according to your use case, and then you can add back a fully connected layer, and you will only train this newly added fully connected layer, right? So the other thing which you can do is you can also add this fully connected layer and some part of your CNN base. So this part will be trainable, right? So this will become trainable, and this will become frozen, right? So you can have a mixture of your CNN base with where few of the layers of your CNN base is kind of frozen and few of the layers of your CNN base is trainable, right? So you will train the weights associated with this part, and also you can train this fully connected layer, right? And the third thing which you can also do is when you have lot of data, right? So this was like number two, and this is like the number three. When you have a lot of data and you have a huge base of images, so what you can do is you can use either like VGG16 and or like ResNet, and then you can throw away the fully connected layer from this models like VGG16 and ReSNet, and then you add your own fully connected layer, and then you can you can train everything in this layer, right, along with the CNN base and also the fully connected layer. So you train the entire model here, right? And this we generally do when we have lot of data, right? So this is we do when we have lot of training data. Okay, and so yeah, this is the three type of transfer learning you can do. And so you when you use this type of architecture, you don't need to bother about like what would be the number of filters or the kernels you have to use, and what would be the shape of those kernels, what would be the size, because it has been seen that in the past data set, people have been using this CNN based architecture and they are getting good results using either like VGG16 or ResNet, right? So with that, you need to bother about, you don't need to bother about building the CNN based architecture. You don't need to put a lot of thought on that. And you can only add your fully connected layer, and you can train only the fully connected layer, or you can also adopt like the point 2 or the point 3 approach, right? So yeah, that's all I have for this video. So in the next video, I will talk about how you can implement this point number 1 in PyTorch, right? How you can implement this concept of transfer learning using PyTorch, and we will use a model which is VGG16, right? So we will add back a fully connected layer, and we will like freeze this CNN base, and we will only touch this fully connected layer, and we will do the weight updates on this fully connected layer. Okay, so I hope you got an understanding what I was trying to explain. Okay, so that's all I have for this video. If you haven't subscribed this channel, please subscribe and also like this video if you found this content helpful. Thank you. See you in the next video.